So in the previous lessons, we learned how to calculate the running time of an algorithm, and we also learned about asymptotic notations as a way to classify these running times into some generic classes. Now in this lesson, we will learn about some techniques and some rules using which we can avoid doing all these complex calculations and still derive the time complexity expression in terms of big O or theta notation. Before we start discussing these techniques, I will make two statements, and the statements are that we analyze time complexity in most cases for A, very large input size, and B, worst case scenario. Now, what can be a worst case scenario apart from very large input size is something that we will discuss later in some examples. Now, if we have a function defining the running time of an algorithm like Tn equal to nq plus 3n square plus 4n plus 2, then for very large input sizes, these lower order terms like 3n square plus 4n plus 2 will become insignificant in comparison to the nq term. So this will be almost equal to nq for very large values of n, or we can also say that thing like when n tends to infinity. And that's why we say that this function after some time will not grow any faster than a function c and q, where c is some constant, and we say the same thing as this particular function is big O of nq. So the first rule that I want to state is that if you want to calculate the big O notation from a polynomial expression like this, then you need to drop all the lower order terms, and you also need to drop the constant multiplier, and you will get the big O expression. For example, say if Tn is equal to 17n to the power 4 plus 3nq plus 4n plus 8, then you first need to drop the lower order terms and just keep the highest power, which is n to the power 4, and then you also need to drop this constant multiplier 17. So this will be big O of n to the power 4. And we may also sometimes encounter time expressions like Tn is equal to say 16n plus log of n, and for higher values of n, log of n will become insignificant, and you can always try to deduce a mathematical proof, but this will be equal to big O of n. So you just ignore the lower order term, which will be insignificant in comparison to n. Log n will be insignificant in comparison to n, and we drop the constant 16. Now let us see some other rules. And the rule is that we can calculate the running time of an algorithm by summing up the running time of the fragments in the program. And we will discuss this using some examples shortly. What we will basically teach you is, by looking at a code, you should first look at the running time for different fragments and then calculate the overall running time. If a fragment of code is a group of simple statements like some declaration, for example, we declare int a, and then we say that a is equal to 5, and then we say that a should be incremented, then all of these are simple expressions. So a fragment of code with all these simple expressions will always run in a constant time, so the time complexity is big O of 1. Now if we have a loop, say for example, and let's say this is a single loop, and inside the loop we have simple statements and no complex function call or another loop. So the running time of a single loop would be the number of times the loop runs multiplied by the running time of the statements inside. So in this case, this loop runs n times, and the simple statements take constant time, so the total time taken is definitely proportional to n. So the time complexity of this fragment, a fragment like this, would be big O of n. And I will create some space for another example. Now let's say we have a fragment which is a nested loop. Now in this case, again the outer loop will run n times, and corresponding to each run of the outer loop, the inner loop will also run n times. So the simple statements will be actually executed n cross n times, and the running time of this particular code will be will be some constant times n square. So clearly we can say that this is big O of n square. This fragment is big O of n square in terms of time complexity. Similarly, if there were 3 nested loops, then in that case the complexity would have been big O of n cube. Now let's assume we have a program like this. Now in this case we have a fragment which is just a bunch of simple statements. We have a fragment which is a single loop, and we have a fragment which is nested double loop, and we have picked up this example from our previous slide. Now the running time of the first fragment, as we saw, was O1. So this is O1, and this is big O of n, and this is big O of n square. And the overall running time of this particular function would be sum of the running time of all these fragments. So this is big O of 1 plus big O of n plus big O of n square. Now once again, when we analyze time complexity, we want to analyze it for very large input sizes. So for very large input sizes, for very large values of n, this part will again become insignificant. So the time taken is actually big O of n square. So thus in a typical program, the maximum running time, the fragment which has the maximum running time, actually decides the overall running time of the program. Now let's say we have a function like this, where we have some conditional statements. So the program is like, if some condition is true, then we have a single loop which will have a time complexity big O of n, and if this condition is not true, we have a nested double loop which will have a complexity big O of n square. Now if control of the program goes to this particular part, it will execute with a complexity big O of n, but if the control goes to the else part, it will execute with a time complexity of big O of n square. As I had mentioned earlier, when we try to analyze time complexity, we always try to analyze it in the worst case. So in this case, if we are not lucky, then we will go into the else condition. The control of the program will go into the else condition, and the complexity would be big O of n square. So that's why we'll say that the time complexity for this particular program is big O of n square, because that's how it is in the worst case scenario. So in case of the conditional statements, you do not simply add up the fragments or try to calculate the time taken as the sum of the two running times, but you pick up the maximum of the two. So we have this rule for conditional statements that pick complexity of the condition which is the worst case. So in this lesson we saw some rules to analyze the time complexity of some very basic programs. In next couple of lessons we will see different time complexity functions and their comparison, and we will also see how to analyze the time complexity of recursive programs. So thanks for watching.